Okay, let me talk about the Carnot cycle. Carnot cycle is a cycle, right? And then this is important for you to draw. So draw, in your paper, draw. Your x-axis is a volume. Your y-axis is pressure. That's my choice. Okay? And do not draw what I'm drawing now because I'm going to delete that, but let me just show that. So I'm starting here. Somehow I extended myself. Go here. This area under the curve is what? It is magnitude of the work, right? This is my choice. Okay? And then when I go back to complete my cycle, right? And that is a work surrounding this. So when I go through this cycle, the area under this envelope, okay? So if you want to draw another one, that's fine, you can do that. This is the whole point for me to decide to do. Choose pressure on the y-axis, volume is in the x-axis, the area under this cycle process, which is an expansion, compression, right? And that is your work. And to be fair, this work is actually my system is my engine, so area is proportional to the magnitude of the work, and that's what I'm getting into. Okay. So Carnot cycle, what are those? This is a Carnot cycle. Let's do that. Carnot cycle is all reversible process. Expansion, compression, everything is reversible. And the reason that they want to do the reversible is, remember the reversible work versus irreversible work, which is bigger? The maximum work that you can get out is a reversible work. Remember this? This is another one. That's a reversible work. Yeah, I guess irreversible work using this external pressure here. That's a reversible work, whereas this is the work reversible. So work reversible is always bigger. Sort of the maximum work that you can get out when things are reversible. So as far as the Carnot is concerned, he is interested in taking what is the maximum work can I get out from this engine? Because that's the one constraint that he has. So that's why things are reversible. And what's my choice? My first choice is what? Guess what? Right? You only know two, right? He only know two. Iso what? Thermal. I guess the expansion, right? And then so we are changing from V1 to V2. Okay. And then what else can I expand? How can I expand? And reversible isothermal, reversible. That's right. V2 to V3. Actually, they use ABCD. So let me change that. To be consistent with my note, would they just use, I don't like this ABCD because now you get confused with the cold temperature and high temperature, but this is the notation that author used. So this is an A, state B becomes state C volume, right? So your kind of successful expansion, you do isothermal expansion first, and then you do adiabatic expansion. That completes my expansion cycle. Then I need to go back, right? I need to go back. So what's my rest of the form? Obviously, isothermal, reversible, isothermal. I guess the compression, right? You need to change the volume to smaller one. So C to D. And then this one is compression. So it looks like we are just putting together that all we know. And I think that's why this was some cadet in the French scientist who just had a little small thesis. He wrote about Carnot Cycle and just being forgotten in the history of the thermodynamics. It was a Lord Kelvin who found this one. And you want a complete cycle, right? And this is a 4-stage process. So your final volume is same as your initial volume. You're going back to your original. And that's the beauty of it. So cycle is the beauty of this. Okay, so if you have if you want to redraw it, you can redraw it too. And let's do this. Drawing this one correctly is very important. I see you guys like doing it a different way, but just do like I draw, okay? So you are using something like a little flatter line like this. And if this is my reference, and I'm going to delete that. If I continue to expand, this is my state A, state B. My initial volume, VA, so I guess a VV, right? I'm expanding this. This is an isothermal, the stage 1. Isothermal. So I just got here. Okay? And if I continue to do this, let's say just isothermal. Reversible is all reversible, so I don't need to re-emphasize that. If I continue to go, it will be like this. This is a sort of the what you guys used to call in the freshman chemistry. This is an isotherm, right? Pressure volume differences when there is a change, keeping the temperature constant. This is an isotherm line. You guys remember that? And then do you remember the chapter 2, when we talk about adiabatic expansion, the pressure versus volume is constant for isothermal, right? What about adiabatic reversible? It's a gamma, and gamma is CPM divided by CVM, and this is definitely bigger than 1, okay? Typically, this is like 3 over 2R, 2 over 5R. So this is, for example, here is 5 over 3. That's bigger than 1. So this one is always guaranteed to be bigger than 1. Okay? So when this happens, this one is actually drop more sharply than they should be, as it would happen in the isothermal. Because it's an adiabatic, the drop is sharper. Does it make sense? Okay. Yeah. So I'm doing the C, and then I need to go back. But now I'm going to just draw another isotherm. This is another isotherm shown up here, and then this one is now you're going to follow this to a stage D. When I asked you guys to draw in the exam, to draw the Carnot cycle, really, it's almost like I'm anticipating at least you draw the diamond. Okay, this is a sort of the idea. Okay, it is not straight line, but at least the slope is milder or sharper decrease. Okay, so this is what it looks like. But the real thing is actually the curve following this line, following P V equal constant line. So, all right. So and then to complete myself, as the going back, and then I finish my task, and I'm going to decorate this graph that I just showed. This decoration graph is much more useful, and it's easy to remember. Okay, there are a whole one of the very complex table that I write it in my note, and you can calculate work and heat and so on to calculate everything. But this concept is very important. So this is what we call, that's the work, right? Right? And then this is an isothermal. The bottom one is also isothermal. And we are going to call this one isothermal at TH, high temperature. This is a colder temperature at TC. Right? So this is isothermal at TH. This is isothermal at TC. Those are the two isothermal processes. So isothermal, so I can say at TH, TC. And what's my also cheating note here? This is a reversible adiabatic. So my Q is 0, 0 on these two processes. So those are the, I guess, the four very symbolic way to show isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Okay. So what this, so now I'm going to use a biggie one, okay? So this is an isothermal. What is my delta U? My delta U isothermal is 0, right? Delta is 0. So your delta U is 0. That's a Q plus W. Right? You remember? And this one is negative for the expansion. Remember that? So you need positive heat to compensate those. So this is do you remember that the expansion temperature is supposed to go down because you are doing the work to the surrounding. This engine is concerned, they're supposed to come down because you are exhausting your energy to the work to the surrounding. But because you are getting an extra help from the surrounding, supplying the heat to the system, you can maintain the same level of your internal energy. Right? So what people draw in many of the cases, let me just get rid of it. They draw this. You essentially need to have QH. Heat has to be supplied on this, and they use an arrow on even onto the diagrams. I'm just trying to show you things. So I'm just trying to figure out the heat transaction. This is a Q is 0, that's fine. And this is heat is coming in, has to go in. So one thing to know, QH is positive. QH is positive quantity. You have to supply heat to the cylinders that are trying to expand to maintain the temperature to be the same. And so the people are trying to visualize this diamond as a system, and heat has to be poured onto the system, so they put this arrow like that. What about this? You are doing compression. Work is positive, but you are maintaining the same levels of energy. So here we go. Heat has to leave as cold temperature we call QC. That's right, right? And yes, so look at that. Heat goes in, nothing happens. Heat goes out, nothing happens. Over a cycle, the net amount of heat is QH and QC combined. And I'm not going to say subtraction because QC by its definition is a negative. So this is a QC is a negative quantity. Just keep that in mind. Okay, keep that in mind. I'm just doing very carefully here. And then this is something that my final interest. I'm interested in Carnot cycle to know how much work do I get, right? This is the work. This is the work. Okay? And they even put the sign like work is going out to the surrounding. So they are doing the work out to the surrounding. They use this even symbol. What's my sign of the work? As far as this work cylinder is concerned, is it negative or positive?
Positive.
Positive. I mean this is a one, right? They are essentially, look at this, right? They are going back and forth. They are doing the work, right? Once they do the work, this one, the work is, I mean this movement of piston moving back and forth, piston move, I move something, right? As far as this is a system that of an interest. Work is negative because you do the work to the surrounding. And that's the same practice, whether it's going back to the one in the net, because of my cycling motion, I'm moving this, right? So I'm doing something valuable to the surrounding, but at the expenses of losing my internal energy. But it's actually doing the work in a negative form as far as the system is concerned. So remember that this is negative. That's why people trying to, the area representing the work with a magnitude, sometimes people do that. But I just put this one in this way. So this diagram, you can also equally see, somebody always said, okay, the Carnot cycle, heat is going in, work is going out, Q is dumped into the surrounding. This is one of the schematic diagrams they put it out. There you go, right? And then there's really the fun part that we know. So delta U is Q plus W, right? So, this, we don't use any second law thermodynamic variable such as entropy here, okay? Because she didn't know, so we just carry out what we know already, and this is a one, right? But now I'm going to do what is called, let me do the over cycle. Delta over cycle. Do you know what's the notation people put it in? Have you seen the notation that changing in the U, well, we are upper bound and lower bound is the same.